Hello and welcome to the video for Chapter 2. What are we going to cover in Chapter 2? The first thing we're going to cover and talk about in Chapter 2 are atoms. More specifically, how they were discovered, their different parts, their size. You will be responsible for knowing some of the people who were instrumental in discovering the different parts of the atoms. The next thing we're going to talk about are the elements. What are elements? We're going to start our look at the periodic table during this chapter. Along with the elements, we're also going to look at isotopes as well as ions and how they change the different types of elements we're looking at. The last thing we'll cover in Chapter 2 are the different trends in the periodic table. We will start in this chapter to use the periodic table as a tool for how we look at different chemicals and elements and chemistry. One thing you will notice when you look at a periodic table is you will notice an atomic number followed by a chemical symbol followed by an atomic mass. The atomic mass describes how much an element weighs. So here we're looking at an example of carbon. Carbon has 6 protons as denoted by its atomic number. Carbon also has 6 neutrons. So protons and neutrons are found in the nucleus of an atom. Protons are the positively charged element of the nucleus, and the neutrons have no charge. As we can see, carbon has 6 protons and 6 neutrons. Each proton and neutron weighs 1 atomic mass unit. So, carbon's atomic mass should be 12. I will write atomic mass units from here on out as grams per mole. That is the atomic mass. So, carbon should be 12 grams per mole. However, if you look at a periodic table, the atomic mass of carbon is actually 12.01. Why is it 12.01 and not 12? The reason is due to what's known as isotopes. Isotopes are elements that differ in the number of neutrons. So if you change the number of neutrons, you change the atomic mass. So how do we calculate the atomic mass for an element? Well, we are going to look at number 76 at the problems in the end of Chapter 2. Number 76, what we are trying to do in this problem is to identify the element. So we want to identify the element. But we don't know the atomic mass of that element. But what we do know are the different isotopes and their abundance in nature. So, this element, one isotope, weighs 135.90714 grams per mole, and its abundance is 0.19%. Another isotope weighs 137.90599 grams per mole, and its abundance is 0.25%. And then we have two more isotopes. One that weighs 139 or so grams per mole. And another one that weighs 141 or so grams per mole. So the abundance of the isotope that weighs 139.90543 grams per mole is 88.43%. And then the abundance for the last isotope is 11.13%. So, with this information, we will be able to ID the element that we're trying to find. So how do we do that? Well, what we do is we take the sum of the molecular weight times the abundance of that isotope, and we just add all those together, and we'll get the molecular weight, or the atomic mass of the element that's found on the periodic table. So, let's look at that. So the first isotope So what we have to do is we have to turn those percentages into whole numbers. To turn a percentage into a whole number is you divide by 100. So the first one is 0.0019. We're going to add that then to the second isotope. We're going to add that to the third. And finally, we will add the last. When we add all of these up and multiply them all together, what we find is something that is about 140.1 grams per mole, or atomic mass units. And if we go to our periodic table and we look for something that is about 140.1 grams per mole, we find that that element is cerium. And so we can use isotopes to help determine the atomic mass of an element. So, for next Friday, what I want you guys to work on is number 77 at the end of chapter 2. And that'll help you practice determining atomic mass from isotopes. So, we have now learned about the atomic mass, how much some things weigh. If you noticed, when I did that 140.1, I did grams per mole. Moles are not just cute little creatures that burrow under your flowers, but moles help us determine how much substance, how much matter is contained in a specific weight. And so a trick to keep in mind whenever we're doing these mole calculations is whenever we want to go from moles to grams, we will multiply by the molecular weight. Whenever we want to go from grams to moles, we will divide by the molecular weight. So we talked about bridge units when we talked about density, bridging weight to volume. Here, molecular weight is another bridge unit. We'll see it'll bridge the amount that is in matter, or that is in a substance, to its weight. So what is an example of this? Here we're going to look at number 83A in the end of chapter 2. We're trying to find the number of moles in 11.8 grams of argon. So, we have 11.8 grams of argon. We know that is what we're going to start with. So let's set up our equation. So we know we have 11.8 grams of argon, and we want to end up with 1 mole of argon. So, since we're going from grams to moles, like I said previously, is that we will then divide by the molecular weight. So the molecular weight of argon is 39.95 grams. So just to double check, we can cross out our grams and we're left with moles. And that is what we wanted. So remember, if something is on top and another number is on bottom, we will then divide those two. When you divide them, you get 0.295 moles. Now, there is an easy way to check our answer, or check our answers when we do these types of calculations. We know for every 1 mole, we have 39.95 grams of argon. So, we started with 11.8 grams. That's a little bit under a third of what the molecular weight is of argon. And so it makes sense that our answer is under a third. So we should just continually check ourselves when we do these sorts of problems. And so then for Friday, I want you guys to do 83B and D, and then 84A and B. Just again, to get us into the habit and into the practice of working with molecular weight to find moles of a substance. The final thing that we can do is we can use moles to then calculate the number of atoms that we're talking about that are in a weight. The way we do that, the way we can talk about atoms is by using Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. Either molecules or atoms, the unit changes depending on what you're really looking at. I'll just put atoms here. You will have to memorize this number. I know I don't have you guys memorize a lot of numbers, and I won't have you guys memorize any of the equations, but you do have to memorize this number. This is a number that we're going to constantly be using, and that should just come off the top of our head. So Avogadro's number is 6.022 times 10 to the 23rd atoms. So how can we use Avogadro's number? So just like the previous example, instead of looking for moles, let's look for the number of atoms in 2.26 grams of mercury. So, we want to start like we did before. We start with what we know, 2.26 grams of mercury. We want to finish up with atoms, because that's what we're told to solve for. So, to go from so before we can solve for atoms, we have to solve for moles. And so if we're going from grams to mole, we'll put our 1 mole here, and we'll have to divide by the molecular weight of the element that we're looking at. Here, it's mercury. So, for every 1 mole, there is 6.022 times 10 to the 23rd atoms. And so we can use a mole to define anything. We could say I have a mole of avocados, which would mean I would have 6.022 times 10 to the 23rd avocados. Or basketballs. So mole is just a way to describe quantity. And so we have 2.26 grams of mercury. And so let's just to double check, our grams cancel, our moles cancel, and we are left with atoms. And that's again what we're trying to solve for. And so what we have is we now have 6.78 times 10 to the 21st atoms of mercury. And that makes sense, again, to check our answer. That makes sense because we have almost a tenth. We have a lot less sample than what the molecular weight is, which means we will have a lot less atoms compared to 1 mole. And so these are just little things that as we practice and as we continue to do, we'll start to quickly check our answers. So we can go from grams to atoms, and the last problem we'll look at is number 89A. And that is, we can go from atoms to mass. And so we want to know if we have 1.1 times 10 to the 23rd atoms of gold, what is the mass? And so again, we're going to start with what we know. And that's atoms. And we want to end up in grams of gold. Right? So we know we start with atoms. What is it that we can use to calculate then mass? We know we need to turn it into moles. And so we have 1.1 times 10 to the 23rd atoms. So if we have 6.022 times 10 to the 23rd atoms and 1 mole of gold. And then, if we're going from moles to grams, we're going to multiply by the molecular weight. So I know that 1 mole of gold is equal to 196.97 grams of gold. So again, let's check it out. Atoms cross out, moles cross out, and we're left with grams. Remember, numbers that sit next to each other, we multiply. Numbers that are under each other, we divide. So, when we solve it all out, we end up with 35.98 grams of gold. I would recommend finding some other problems in the back of Chapter 3 that are very similar to these, just so that you can get a little bit more practice.